be doing relations. And then I was just going to have a lot of lessons within this lesson. So we're going to talk about a lot of things that help us get to what relations are. So we're talking about ordered pairs, where an ordered pair is a pair of objects written in a specific order. So you have to have a specific order. For example, if you have A and B, the first element here is A, and then the second element is B, right? Take note, I didn't write it in set form where you'd have A and B. I wrote it in, you can say point form, where this is now an ordered pair. Or if you were to think of Cartesian planes, if you have A being 1 is to 2, so this would be 1. Oh, sorry. Okay, never mind. But you would have 1 is to 2 and draw the dots on 1 is to 2, right? So it has to be in an order, right? So here basically order matters. Another example or another thing I'd like to add on, if you have 2 is to 5 and 5 is to 2, these two are not equal. That's what I basically meant. So if you have a Cartesian plane like that, and let's say that's 5 and that's 2. 5 is to 2. So the first, okay, let's do 2 is to 5 first. So we're doing this in white. 2 is to 5. So x is 2, 5 is y. And you would have somewhat a dot there. If x is 5, just gonna elongate this. And y is 2. So if x is 5 and y is 2, you would have another thingy going on here. So these are two different things. And hence why we say order matters. Order matters for ordered pairs, right? In real life, for example, if you think of GPS coordinates, when you have latitude is to longitude, if you swap them, you would end up in different locations. So order does really matter. Okay, let's I wanted to say these two are not equal, but these two are equal. So with sets, order really does not matter, but for ordered planes, order does matter. So if you're doing Maths 1503 or linear algebra, remember when you're doing vectors, order does matter. Okay, let's talk about the Cartesian product. So a Cartesian product of two sets is the sets of all possible ordered pairs. Remember what an ordered pair is, and then I'm just going to read the definition again. A Cartesian product of two sets, remember, of two sets, right, is the sets of all possible ordered pairs. So for example, if you have A and B like this, the Cartesian product of A and B would be all possible sets, but of ordered pairs, right? So if you think of ordered pairs, you'd have to go 1 with A, and then 1 with B, and then after that 1 with C, right? So you're going first element, and then you're multiplying it with whatever that's in B. So whatever that's in B is going to be the second element because you're taking A first and multiplying with B. Secondly, you would have 2 and A, and then you would have 2 with B, and then 2 with C. So I'm just going to write it quickly. So the set or the Cartesian product of A and B would be the 1 with A. Now this is an ordered pair. 1 with B, 1 with C. Then you have 2 with A, 2 with B, and 2 with C. Right? And remember, for sets, you can just mix up. So maybe this ordered pair, you write it here, and this, you write it. But inside the ordered pair, it has to be exactly as is. You can swap with sets, remember, but the ordered pair has to remain the same way. So I wrote down an important formula that you can follow if you're doing Cartesian products that you quite have to remember. I'm going to explain what I mean. So you check the cardinality of M, and then the cardinality of B, and then the cardinality of the Cartesian product would be the product of the values. All right? So this basically means the Cartesian products of A and B should have the M and N elements. For example, if you have something like this, so if A is this and B is that, they ask what is the cardinality of A and B. Just let's calculate it here. So cardinality, let's first work out. So if A is the set 1, 2, 3, this would mean the cardinality of A is equal to 3 because we have inside 1, 2, 3 things. So that's the cardinality. And if so B's cardinality, B's elements is X and Y. So if we were to find the cardinality of B or the size of B, it would be 2. So now the cardinality of A times B is 3 times 2. which is 6. So that's the cardinality of A and B. Obviously, you don't have to write this. I wrote those down to remind myself. Secondly, they want us to determine the Cartesian products of A and B. So if you have A times B, Cartesian products, remember A was 1, 2, 3 and B was xy. So you would have 1x, 1y, and then you have 2x, 2 and y. You have now 3x, 3 and y. So I want us to check something. Why the formula for cardinality actually we were finding it, right? So if you count these elements, you'd have 1, 2, 3, 4, 5, 6. And what does this tell you? It tells you that for you to, if you want to check if your answer is correct for the Cartesian products, you can find the cardinality of each, and because of the cardinality, you would know if your answer is or your Cartesian products elements are correct or not, basically. Okay, now let's talk about relations, right? So we've been talking about the cardinality, we spoke about the Cartesian products, and we also spoke of the ordered pairs. So a relation is basically any subset of, or any possible subsets of the Cartesian product. So this is how you write it. Obviously, in theoretical computer science form, a relation is any subset of a Cartesian product, and this is basically what I've simplified here. So suppose, for example, you have this A and B. The cardinality of A and B would be this. If you want to, you can check. You have 3 here, you have 2, and those 2 would give you 6. This is 1, 2, 3, 4, 5, 6. So that's the cardinality of A and B, and that's the Cartesian product here written of A and B, right? So any relation could be from this. Remember, a subset is anything that's less than or equal to that big thing that you have. So a relation here could be, for example, let's take the 1 and A, 2 and B. So it can be this, it can be, let's just take 1B, it can be this, or it can be 1A and 3A. So can you see that everything that I've taken from here is indeed here? So a relation basically means a subset of any Cartesian product. Remember what a Cartesian product is. A Cartesian product is a set of it's a Cartesian product of 2 sets is the set of all possible ordered pairs. So 2 sets, meaning this set of A and set of B. And then right now, let's say, for example, here I have A here and I have B. And this basically is the Cartesian, not really the Cartesian product, but it's the cardinality within this. So from this, I've created a little subset. And that subset that you create from a Cartesian product is called a relation. Okay, from relations, we have a lot of different things. But honestly, there's something I need you to pay attention to, which I might be repeating myself, but can you notice that not every pair has to be included? Like if you think of subsets, not every pair should be included or can be included. It just has to be there. Something of that big set has to be in that small set that you're creating, right? And that's because a relation is any subset of the Cartesian product. So it has to be of a product, or you have to see an ordered pair. Okay, let's talk about things that you can find in or within the relations. So within relations, you can find domains, codomains, and ranges, right? So suppose you have this relation, and we just basically normally or usually use this big R to know as a notation, or yeah, as a symbol to show relation. So I'm just gonna always refer to that. Okay, suppose you have this type of relation. Remember, a relation is a set or possible subset of the Cartesian product, right? And then they ask you to find the domain. In this, a domain basically is a set of all first elements in each ordered pair. So in each ordered pair, the first element here is A, the first element here is 2, and the first element here is 3. So the domain would be a set of all those first elements. So a domain here would be 1, 2, and 3. Okay, and then secondly, we talk of the codomain, and then thirdly, the range. So a codomain is the second set in each ordered pair. So if you look at R, the second set in each ordered pair would be A, B, and B. So you're right. There's a set there, A, B, and B. Remember, B is the same as B, so you don't have to write it twice. You can just write it like this. right? So this would be now a set. If you have something like this, when we get to functions, you'd basically find out why this is not a function, right? And then a range is only the values used in the second set. So only the values used in this case would be A and B in the second set. So a codomain would be, let's say if you were to look at, let's say we were looking at this big Cartesian product and we see that we have, oh, we have A, B, okay. Okay, let's say we had a C as well, right? A C in the second set. The 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 codomain would be what we have in here, right? So your codomain would be what we have, let's say here, everything in the second set, right? And then the range would be only what's in here, the given thing that we're supposed to look at. So I don't know if I'm naming it correctly, but that's how I know. Let's talk about the inverse relation. And I wrote here some notes. The inverse relation is obtained by reversing every ordered pair. So for example, if you have R, or the relation 1A, 2B, now, and the inverse of that would be reversing everything, or reversing every ordered pair. So you would now have A, 1, B, and 2. And because obviously you've reversed everything, it's no longer equal to the original R. And from there you have now the inverse, right? For example, if you think of pure calculus, if you have maybe a parabola like this, let's name this R, the inverse of this, I think, would be somewhat like that, which obviously um, this is more like you're not a function. So this R inverse is not a function in this case. Or if you think of straight lines, if you have maybe a line here, if you flip it, so flip it, the inverse would be somewhere here. Think. And then if you maybe have an exponential function, let's say you had something like this, the inverse, I think, would be something like, don't remember, I did my grade 12, like the inverse would be something like that. Okay, let's talk about the composition of relations. So suppose you have R as this and S as that. Obviously it's a relation because you have a pair of Cartesian products, and it's not obviously everything because they're telling you it's a relation. So it's not the whole Cartesian product, it's just a subset of a Cartesian product. So now if you were to determine the composition, we use that little circle there. The composition in this case would be, okay, I think I write it here. So it would be what you're doing. Okay, so what you're doing is you would take one from here, so this one, and then that, right? So because you have two A's, we don't need this A. You just take one here, and this would be the first element, and then the X would be a second element, right? And then going from B, so the second ordered pair actually, you would take 2 and Y. You would have 1 and X, and then you'd also have 2 and Y, right? So something like that. So you're basically going this way. You're going 1, and then you leave the A, you take X, and then you go 2, you leave B, and then you take Y. So 2, cancel the B's, take Y, 1, cancel A's, and then take X, basically. So that's how you do compositions. Let's talk about the properties of relations. So for number 1, there's reflexive, and that basically means every element relates to itself. So if I didn't write the example here, but I think this would make sense. So if you have the relation R, and then inside the ordered pair you have 1, 1, 2, 2, 3, 3. This relation is reflexive because every element is represented as A, or you can say because every element is basically 1, 1, 2, 2, and 3, 3. So you can write it like that. And then secondly, we have irreflexive, which is quite the opposite of that. And that's when no elements relate to itself. So if you maybe have something like this and this, there's nothing really like 1, 1, 2, 2, or 3, 3. So the relation is reflexive because no element appears as itself. And then we talk of symmetric. This is whenever A or B is an element of R, then by default, BA has to be an element. So if you have this, quite the opposite, or the, what would you say? the inverse. So obviously, if you think of inverses, inverses are more like like a symmetry thing going on. So everything that's in there should be quite in here, like the symmetry of that. Right? So if you have 1 2 and 2 1, can you see that this is flipped? Right? So this is symmetric because every ordered pair is the reverse that belongs to the relation. Right? Or you can say every ordered pair is written in reverse. So if you have, for example, AB, or you can say every ordered pair is written in the form of AB and BA. Right? So you can say something like this. Anti-symmetric is the opposite of symmetric. So if you don't have anything like this that is written in reverse, that's by default anti-symmetric. If A, B, and so I wrote it here, if A, B, B, C belong to a relation, then by default A, C should also belong to A. So if you have A, and then B is in both, so by default A, C should be also quite a pair, and that is transitive. It's not really the same as symmetric, because if you think of symmetric, you would have maybe instead of these two, you would have B and A, right? So that would be symmetric. Okay, and it's also not reflexive, but you can say it's quite irreflexive because nothing really here repeats itself, basically. So if you have maybe something like this, or something that's quite irreflexive, R, you would explain it like this. R is not transitive to the relation, since 1 2 and 2 3 belong to the relation, but 1 3 does not belong. So remember, because you have 2 here and 2 there, by default you can still have 3 and 1, basically. So it's not transitive. Trichotomy, I think it's trichotomy. So this basically means for any two elements, if you, let's say, have A and B, only one of the three is true. So if you have maybe, so A cannot be smaller than B, and at the same time B is smaller than A, and then at the same time B is also equal to A. It's not really true. Only one can take the spot. For example, if you have 7 and 4, so 7 cannot be smaller than 4, right? But 4 is smaller than 7, so we take that. 7 is not equal to 4, right? So if you want to explain this, you would say um, so this kind of trichotomy passes. So you would say this smaller than trichotomy is satisfied. So that is how you basically do relations. Please do know your properties by heart. Know what an ordered pair is, know what a cardinality is, know what the Cartesian product is, know what a relation is, and how to explain those things. Also know how to justify if properties are true or not, and that's basically what you have for relations. Next time we're going to be doing functions, where it's quite deep. It's relations but in depth. So stay tuned for that.